second one, right? For example, this may be a graph signal. So how will I represent it? Can I write its weight matrix? Yes, I can write its weight matrix in this form. So when it's basically, see, remember one thing that depend upon the vertices. So if it's a three vertices set, so it will be a 3 by 3 matrix. So what will be the value? The value we will write here. We are writing the weight matrix. We have understood the vertices, we have understood the edges. Now we want to write the weight matrix. It will be, I will explain everything. 0 is 0. This is 1. In the second matrices is connected with 1. No, it is not connected. That's why it is 0. A second matrix is connected to the third one. Or no, second is connected to 1. No, second with itself, it is 0. Is second connected with third one? It is 1. Now we come to the third vertices. Is third vertices connected to 1? Yes, it's connected. 1 is connected to 2. 1 is this connected to this one? No, it is 0. What is this? This is basically the weight matrix. What we write? This is basically the W. So is this part clear? See what we are doing here. So we have taken basically a one very small graph signal, which consists of the three vertices 1, 2, 3. 1, 2, 3, one where one is connected to 3 and 3 and 2 are also connected. So when we are writing it, so this is basically the W. I hope everyone is with me. Are you able to understand this weight metric? Very, very simple, basic, but very important to for building the concept. Is it clear? Okay, so I make another graph signal, whether I check it, whether are you able to make a correct weight matrix or not, right? Because what we are emphasizing upon the representation of a signal. So that four vertices are there and these are basically the connections. So now we have to make a matrix. So it will be definitely when it's a four vertices, so it will be 4 by 4 matrix. So see, 16 values will be there. So can you tell what will be the value, first value here? Whether will it be 0? Yes, 0, 1, 0, 0. Somebody has write it because with 2 it is, Krishna has write 0, 1, 0, 0. Someone has write 0, 1, 0, 0. This is so. First we check out whether it will be the. Just a minute. It will be because one, there is no connection. We are not taking connection with itself. So it is 0 only because 2 is connected with 1. So it is 1. If 1 is not connected with 3. So it will be 0. 1 is not connected with 4. So that is also 0. So it has been right. What about the second one? Krishna has written it is, one has written 0, 1. So what we write again, we check with 2 is connected to 1. Yes, it is connected to 1. Is 2 connected to itself? No, we are not taking self interconnection, so it is 0. Whether 2 is connected to 3? No, it is not connected, it is 0. Whether it is connected to 4? Yes, it is connected to 1. So this is 1, 0, 0, 1. So Suman, you may correct it here. What about the third one? In third one, see what we are seeing here. That third, whether is it connected to 1? No. So that is 0. Whether third is connected to 2? No, it is not connected to 2, it is 0. Whether third is connected to 3? See, we are not taking self connection, it is 0. And then finally, it is 1. Then we come to the last one, fourth one. In fourth one, if we see whether that fourth is connected to 1, no, it is not connected to 1, it is 0. Whether 4 is connected to 2, yes, it is connected. Whether 4 is connected to 3, yes, it is connected. Whether 4 is connected to 1, so this is 0. So yes, so Krishna has written correctly. What about apart from Krishna and Suman? I hope everyone would be able to understand. Right? So what we but here we are taking one assumption. What assumption we are taking? That all the edges are of the same weight. To make the thing simple, initially we are considering that all the wherever the edges are, if edges are there, its weight is 1. If edges is not there, then it is 0. What we call it? We call it basically the binary weight relationship. It is not necessary. It may be the one, see the, so it is the very, very simplistic view. But here we are able to understand the graph signal. So can you tell me what is the value of the graph signal here? Is this matrix only or is it different? I want but some participation initially so that these concepts are clear. I am asking that what is the value of this graph signal which has the four vertices? Is this the value? Is this 4 by 4 matrix? Can we derive out it from it? Or is it different? See, remember one thing that whenever we are saying this, basically the graph and signal are the two things. Graph basically tells about the interconnection, right? But signal value, graph signal value is different from it. So how it is different? So from this 1, 2, 3, 4, only we are able to know it is Krishna is saying graph signal value associated with nodes. Yes. So we need some additional information. What is the value basically at the node 1, at node 2, at node 3 and node 4? And we all will have the value. So what will be the value? So uh, can we write it here? Yes. It is value, for example, at node 1, it may be value 2, at node 2, it may be 3, at node 3, the value may be 5, at node 4, the value may be 3. Any value we are taking, just we are trying to understand the representation. So it will be 2, 3, 5, this will be the value. So what we say, what in the our slide, that was basically the x1, x2, x3, x4. Remember, this is the additional information which is not related with the basic structure. This is independent information, right? So this is the one. Okay. So we move to the again slide board. I have to interchange between the slide and here. So any question? Now we take up the another case. Change here. One, change, new, new. Hmm. Yes. Yeah. Hmm. Hmm. Okay, so now we come to the another graph signal, right? Write it one, write it two, write it three, write it four. This is another graph signal. Again, we want to make the weight matrix. So, but here what is also mentioned here, that this weight is 1, this weight is 2, this weight is 4. So can you write the matrix, weight matrix? This is not basically a binary weight, it is a open weight. Please try to write it even if you are not confident so that you can find out. So first step, see, it will be basically 4 by 4 matrix. We are asking basically for weight matrix. So 0, 1, 4, 0. Someone has written whether is it the correct one. So 1 is connected again. See, 1 will be always 0 because we are taking assumption that 1 is there is no self connection. In the graph signal processing, we are taken some assumption. 1 is connected to 2. Yes, it is connected to 1. It is 1. Is 1 connected to 3? Yes, it is connected to 3. It is 4. And whether is it connected to next one? It is 0. So someone has mentioned yes, 0, 1, 4, 0. And then second one, the second node is connected to first one. Yes, it is connected. Whether second is connected to the third one. Second is connected to no, it is not self-connected. Whether second is connected to the third one. Yes, it is connected. Here value is 2. Whether second is connected to 4, no, it is not connected to 0. So this way people are reaching, right? So yes, Suman has mentioned correctly. It is 4. Third is connected to first one. 2. This is this next element. It is 0. This is 0. Fourth is basically not connected to anyone. So it is 0. It is 0. It is 0. It is 0. So what you are seeing here that this is basically a matrix which is a symmetric matrix. When you are seeing it 0, 1, 4, 0, if I transpose it, if I take the transpose of it, this matrix becomes the same. It's 0, 1, 4, 0. If I make it this row as a column, it is same. Then I take the next row 1, 0, 2, 0. Even if I make it, that is also the same. Yes, if you would have identified another thing. So weight matrix is basically a symmetric one. Weight matrix is symmetric matrix that we are observing. And weights are not limited. It can, but remember one thing, all the even what we are saying here, that it is basically in some cases what, so this is basically undirected weight matrix where direction doesn't matter. Even there may be a case where direction is there. For example, this is there. One is directed to 4. One arrow is there. What do you mean by it? It means that there is a relation that 1 is connected to 3 by 4 weight, but 3 is not connected. So what will happen in that case? In that case, 1 is connected to 3, here it will be there, but at this point, it will be 0. Remember, when we are taking undirected weight matrix, they are symmetric, but when we take the directed, where direction is also there, then they are not symmetric. But whenever we are discussing the graph signal processing, our in this course as well as for the beginners, we will always use the undirected weight matrix. We are not going to the directed weight, right? So whatever theory we will read in our context, that is undirected. Any question, if you have, please mention it in chat box. So what we have understood basically the representation of the graph signal. What does graph signal consist of? Graph signal consists of basically vertices. Graph signal consists of the edges which connects the nodes and the weight. Weight basically which tells about the strength of the edge. Apart from it, apart from the structure of the signal contains itself, signal itself as the value, and that value is basically that is additional to 1. So we say that what is the value at the node 1, what is the value at the node 2, so that will be there. Is it understood? If it understood, then we move to the slides. चार्जिंग नहीं इसकी तो बटन और ये तो ऑन है ऑन नहीं हुआ So now coming to the slide part. So now what we are saying, again moving to slide. So now what we are saying, geographical network, traffic network, brain network, these are basically the different network. Again, see, we have till this part we have covered, then the network centrality, community. So these are basically the different type of networks are given, where different type of connections are there that has been emphasized here. Now what we see is the graph structure data are pervasive. They are available everywhere. So what we are saying that, for example, this is a monthly average temperature collected at 299 stations of the Brazilian meteorological temperature data set. What is this one? This is basically air. So these places, different places are there, which are the nodes, and the temperature value is basically the signal. What is the temperature at that place? That will tell the signal value. What about the edge? Edge means definitely when some place is directly, it is basically the geographical proximity between the different regions. See, because we can understand that if some two places are in the nearby region, then definitely they are related. They have the same weather phenomenon. That's why we are saying edges as basically the geographical proximity between the region. In the same way, another way, it is basically a traffic network, lower one you are seeing. Here, basically, what are the nodes? Nodes are basically the road junctions. What are the edges? These are basically the road connections, traffic. So what we are telling? We are telling that we can represent the actual situation in the form of the graph very well. Whether it is a temperature sensor data or it is basically a road network data. Now coming to the one, see, image also can be represented in form of the graph. So even see in my PhD thesis work, I basically did the work on the facial expression. There, I represented the facial image is in form of the graph. So what is the value? So if you see here, this is these pixels are basically the nodes. What is the edges? Spatial proximity. Remember, spatial proximity means the pixels which are nearby to each other are more correlated with each other because see, they are all part of the one figure. What do you mean by the signal? Signal means the pixel value. What is the intensity of what is the intensity of that pixel? So now hope see. So can somebody tell what will be the pixel value of a grayscale image? We have covered it in the day before yesterday. What is the range of the pixel value in a grayscale image? It is 0 to 250, I guess, for the 8-bit. Because, right. This is the one. Another, we take up the another example. So what we are telling that graph structure data are very much available in the actual thing. So this is companies are there. This below network is there where companies are as a nodes. What are the edges? Co-occurrences of companies in financial nodes. Remember the best thing about the graph is that you are the one who define the edges. Edges means on what basis you want to correlate the two things, right? So this in this example, it is telling, see, remember two companies are there. It is not necessary that if some company is in geographical proximity to the another company, they both have the same nature. It is by chance also. Because one company has taken is situated at one place, another company is situated at one place, and it is by chance only. It doesn't mean that they have some relation. So how we are defining the relation? It depends. So somebody has defined the relation. It is basically a co-occurrence of companies in financial news. It may be that whether the product they are making, whether the product if it is the same or if it is related one, then also we can say that they have the edges. Please remember one thing that you need to define the edges as per your objective. What you want to extract, what information do you want to extract from that signal? What do you mean by the signal here? Signal means we can say that the stock prices of these companies. Remember this type of flexibility in the graph where you can define the edges based upon your objective makes a graph very useful too. Another example you can see. It is now we take about our human network, our social network. For example, so what we are saying here that nodes are the individuals. What is the edges? Friendship between individuals. If somebody interacts with them or somebody knows another person, or we can say somebody is in a friend list, then there is a edge. What do you mean by the signal? Signal means it is basically the political view. So what will be the political view? The political view here, it can be that how much you are politically oriented, how much you are politically inclined. You may be a politically neutral person, On a scale, it may be 0, it may be 1. You are very less interested in the politics. It may be value of the 5, that 50% you are okay. It may be the value 9, that you are very actively participating in the politics, in the political activity. Remember, this type of data, graph structure data, has been used to forecast the things for the machine learning during some of the elections, like the Britain and the Europe. So people complained also about the data privacy. So remember, that's why the graph signal becomes very useful, because you can define the signal as per your convenience, as per your interconnection, and as soon as we define it, then we are able to represent the signal. Now coming to the another type of graph structure data, which is basically a brain. The below signal you are seeing the brain. So what you are seeing here, that nodes are basically the brain region. Remember, keep one thing in mind. It is not necessary that node is need to be at some point only. No, see, it may be a collection of regions. That's why, because see, what will happen if I will take the every point in the brain region as a node? It will be a very big network. What will happen if it will be a very big network? See, for example, regions are basically 1,000. There are 1,000 points in a brain. Then what will happen? Then my matrix will be 1,000 by 1,000. It will be very difficult to compute the anything, to do the any operation. Then what is the way? Then I take basically some region, so it will be a limited one. It will be a limited matrix. So what we are see, even in a region, we say that almost all the activities are similar. For example, in this region, it may not be as much that accurate if we take the separate node, but overall it provides a very much flexibility in the computation. So what we are seeing here, so here we have defined the 5 nodes. 1, 2, 3, 4, 5. In some literature, it is also mentioned as the super node, right? Where we can take the collection of the vertices. But here we are directly saying that it is a brain region we are considering as a node. What about the edges? Edges is basically a structural connectivity between brain regions. How your brain regions are connected? Again, see, because remember, one brain region, because information is passed from the one region to the another one, so they are structurally connected. So we are saying if something is structurally connected, then there is a edge. If there are more number of, if there is a deeper structure connection, then the weight of the edge is higher. What do you mean by the signal? Signal here is basically a bold time series. Bold time is basically a voltage. How much voltage or how much activation is there? Blood oxygen level dependent time series. What we are saying, this is bold time series. Where it is used? It is used in basically fMRI. When we want to analyze the data, then this type of representation becomes very useful. You will see the things when you will type the in the Google graph signal processing plus fMRI, you will find many papers. So what we say, predictive approach using GSP. We say that the graph nodes defined by a brain parcellation. So remember, in the analysis of the brain regions, the graph signal representation has become very useful. Graph edges defined by functional or structural connectivity. See, earlier we took up basically the structural connectivity, something is connected, but many times it is, see, things are not structurally connected, but they have the same type of functionality. When they have same type of functionality, then we say that they both are very much correlated to each other. Then we say thereafter feature extraction of brain connectivity using GSP. So what type of features we want to extract out? See, we want to extract out the features that if this type of brain is there, how is it going to behave? We will see the applications later. Feature selection and supervised learning. These things are able to classify the two functionality of the two brains here. So again, now you have seen this word that GFT and the graph wavelet. How do we compute this value? So to compute this value, we need to understand some more fundamental. What are those fundamental? One very important fundamental is this matrix D. What is this matrix D? This D basically represents the diagonal matrix. What do you mean the diagonal matrix? Where diagonal elements are non-zero. What you are seeing here? You are seeing here that it is 1, 3, 4, 2, 2. Only the diagonal elements are non-zero. All the elements are zero. So how do you, now question arise, how do you calculate the diagonal matrix? The diagonal matrix is simple. Diagonal matrix is computed from the weight matrix only. How do we compute it? We add up all the values of the weight matrix and we put that value at the diagonal element. So what we are saying here, for example, this 0, 1, 0, 0, this row and this column both are same. So we will add up all the values, and when we will add up, what will be the value? Just as Suman has mentioned, it is adding weights of each row or each column. It is the same thing because it is symmetric one. So it is 1. What about the second one? In the second row, when we will add up, what will be the value? It is 3. Is it understood by everyone? What about the third one? Third one here, we are mentioning. Yes, someone has mentioned correctly. 1, 2, 3, 4. I hope it would be clear to other participants also. So can you mention all the value here? How many nodes are there? 1, 2, 3, 8. So can you tell the fourth one? Fourth diagonal element. What will be the value? It is 2. Fifth diagonal element. Apart from someone, I am seeing nobody is answering, or whether they are not answering or they are not able to answer. Yes, it is 2. Can you tell about the eighth row? Eighth one. Eighth is 1. Yes. Yes, correct. So this way you are able to calculate. So what we are saying that this diagonal matrix, yes, good. Ruchi has also responded. I hope see it is simple one, but it is very crucial thing that from the W we make a D matrix, diagonal matrix, and then D minus W is L, which is equal to basically Laplacian matrix. Please note it here that it is here undirected graph. Here you are seeing it is undirected graph. What do you mean by the weighted graph? Weighted graph means that there is a different weights are there and which are not binary in nature. Remember, whatever mathematics we are doing here, L equal to D minus W, it is only based upon the structure. No actual signal value is used here. Why we are doing it? We are doing it basically so that we are able to take into account the interrelationship of the different components of a signal. Ruchi has asked a question. For directed graph, we use some other, we can, for directed graph, we use some other. Achha, for calculating the D. No, for calculating the D, it is the same, but only in that case, we do in the same way. But remember, there, what I am saying, the mathematics is a bit different. How we remember why we are calculating the Laplacian matrix, because we want to define the frequency domain. But directed graphs, it's a bit complex mathematics. We will only, people are doing it, but only bit complex one. So at this stage, I don't want to introduce it, because even if you take into account the undirected graph only into our current research, it is sufficient enough to give the better result than the current algorithm. So after the L equal to D minus W, another thing we calculate the L norm. What is this L norm? Laplacian norm. This is equal to D minus half, D minus W, D minus half. So not only one Laplacian is there, this one is also there. This is, now we taking the same graph signal. Now we are saying F1, F2, F3, F7. See, what is this value? See, please try to understand that this F1, F2 are basically the actual signal value. Right? So what is uh, how we are defining basically graph signal? Graph signal, we are defining that vertices has some real value. What do you mean by the signal? Signal means that the vertices has some real value. What is this value? This is F1, this is F2, F3, F4, F5, F6, F7, F8. Why in this way? Because we have numbered the graph in this way, V1, V2, V3. That's why in the same way we have defined the graph signal. So this is F. F we are using it. So what so what do we want to say here? That if we take the Laplacian and Fi, it is equal to the Wij Fi minus Fj. What is it? These are the some relation which has been obtained. So what we are doing here, this is basically L. We calculated the L here, 1 minus 1 0 minus 1 3, and we are multiplying L with the Fi. Remember one thing, that when we are doing this operation, then it is an operation between a matrix. So our L is basically 8 by 8 matrix, and this is basically a column vector. Column vector F1, F2, F3 in this way. So this is the one. What is this? LFI. So these, when you see this paper, you will able to find out the different relation with different type of mathematical relation. In the same way, another very important F transpose LF. When you calculate this value is basically a measure of smoothness. How much smooth your signal is. What do you mean by the smoothness? Smoothness means that how, see for example, see smoothness means basically that for example the value at 1 is positive, at 2 is positive, and 3 is negative, and 4 is positive. It means the fluctuation in the value. It means the change in the value. that can be measured with the help of this magnitude F transpose LF. So, very some important relationships have been established and they are very useful. Where do we use where is the smoothness etc. matter? Smoothness etc. matter when we apply the different type of filter. So anyway, it is one type of mechanism to know the smoothness. Any question till this point? Because it's a bit new topic, so I want that it should be participative. If you till this part now we are very clear about the representation of a signal. If somebody asks me to represent any type of graph signal, I am able to do it. Not only I am able to represent my graph signal, but I also am able to do the different operations. See, what do you mean? How does the representation matter? Representation matters because it allows us to do the different type of mathematical operation easily. What type of mathematical operation? For example, I am able to calculate the smoothness of a signal by multiplying with the F transpose with the Laplacian matrix multiplied with the F. This is elementary mathematics. So nobody has a question. So, so what if the node values are not scalar but vector? So question has been asked from the Krishna. See, remember one thing. See, if you see this definition of graph signal, remember very important thing. This is all the way we have been defining we have been uh, redefining our earlier DSP. So these signal notation becomes very important. See, please try to understand what is it is saying. It is saying that this F is basically mapping from vertices to a real value. So it is defined only that it's a real value. Krishna, it will always be a scalar only because we have defined function in this way only. This is the definition. So this is basically the meaning. What do you mean by F? F basically here vertices map to the value R, which is a real number. So see, that's why we are saying when you will go through, I will also share you the very base paper, core paper of the graph signal processing. I think emerging field of the graph signal processing. It was in 2014, and it is been one of the paper which has been maximum cited. I think it has been cited around 8,000 times. There, all these mathematics is very easily available. But most of the time, see, we are using actually the MATLAB, Python. We are not accustomed to read these things. So that's why this is very fundamental but very important. Any other question if you have apart from Krishna? Krishna, has it been answered? So see, what is the key thing here that when we are able to represent our any signal, for example, so what did I do in my research work? Basically, I represented the image in the form of the graph with these notations, and then I did the operation, different type of mathematical operations on that image, and I got very interesting results. That was my whole thesis. My thesis was basically some studies on the analysis of facial expression using graph signal processing. So if there are no questions, we move to the next. So what we are saying here that where there are some important properties in the L, in the Laplacian matrix. What are these? That L has a complete set of orthonormal eigenvectors. What is this? This is basically if you see if you decompose L, it will come into this form. This is X, this is multiplied by this one, this is eigenvalue set, and this is transpose. What we say that these eigenvalues are usually sorted increasingly and they basically represent the frequency, that how many frequencies are present. And what are these values? These are basically the bases. These eigenvectors are the bases. For example, when in the Fourier transform, when you represent it, different exponentials are the bases. Here, these eigenvectors are the bases. And what is frequency? Frequency is basically represented by these eigenvalues. It is bit mathematical, but not very difficult one. Remember, the objective of this workshop is to introduce you to the new applications of the DSP without going into the deep mathematics. But mathematics is essential. So that we are seeing, what we are seeing here, that L is basically consists of this X multiplied by eigenvalues and then X transpose, where X transpose are the bases and these eigenvalues are basically the frequency. See, once we have defined the frequency concept, once we have defined the basis, then we are able to find out the transform. What is the transform here? Here we are saying about the graph Fourier transform. What is the um, what we are seeing in this figure? In this figure, we are seeing here that this is x0, x1, x50, that these are the different eigenvectors. When we are seeing the different eigenvectors, so if you see x0, x1, x50, if you notice the change here, that in the x50, there is a lot of variation in the magnitude of the different vertices. While in the x0, there is no such change in the magnitude of different vertices. In x1, it's a more than x0, but in x50, it is maximum. So remember, representation is one part. When somebody asks you that, you also define some concepts. It is the same paper, the emerging field of signal processing on graph. If somebody asks you, can you find out the Fourier transform or better graph Fourier transform of that signal? Because remember now, uh, after the representation, we try to find out the frequency domain of that signal. So that has been defined. That is basically XL multiplied by F. What do you mean by XL? It is the same eigen vectors basis. And it is multiplied by F. What is this F? F is basically the signal value at the different vertices or the nodes. Please keep in mind vertices and nodes are equivalent to each other. So what we are saying here, that in this graph Fourier transform, we are able to plot the different frequencies lambda 0, lambda 1, lambda 2, lambda 3 till the lambda n minus 1. What is this capital N? Can someone tell? What is this capital N? Capital N, you are seeing here that when we are plotting basically the different eigenvalues, capital N is basically the total number of vertices, right? Yes, it is the number of nodes. So when you are so what we are seeing here in this figure, in this right hand figure, what you are seeing here, that in the graph Fourier transform, you are able to know that which frequency is present and how much and which frequencies are dominant. For example, lambda 0 is very much higher. What about this lambda 1? This is there. Lambda 2, lambda 3, lambda 4. So finally, what does the graph Fourier transform provide? Graph Fourier transform provide the how many frequencies are there. What is the component of the different frequencies? This is the key diagram. So is it clear? Almost now we have been going through the DSP. Again, it's new DSP. But when we are going through the new DSP, you need to be bit clear what is the basic mathematics, how those people have derived. It is actually a very, very good revision of all the basics. See, yesterday some students had notion कि हम that Pachori sir is uh, discussing old things. But remember one thing very, very clearly. Nobody is going to share with you the latest thing which they are publishing, right? But when they discuss the old things, see, then you are able to know the basis, how the things actually work, how the things actually are derived out. You can never ever build upon the basics if somebody is telling, even if somebody is telling you their new result. Some participants have a notion that okay, somebody is presenting the old fact. But remember, as a learner, we will able to make the change in the research. We will able to make the fundamental only if we are aware about the basic thing. In the same way that when we are reading basically the graph signal processing, you need to be very much aware that what is the frequency concept. What does happen in the Fourier transform? It's not simply a formula. So I think we can take it's a break time, but see, please try to think upon those things. It's a very, very small literature. It's not a big literature, but very with full of potential. So if you have any question, so we will meet at after 10 minutes or 10 or 4:10, right?